Hello, Bacho, and welcome. Today we are going to tackle a very important topic from your Unit 3, Current Electricity, the drift of electrons and the origin of resistivity. We'll make this so simple, I promise you will understand it for life, and every single point will be perfectly exam safe. Chalo, let's begin.
So let's start with a little mystery that I'm sure you've all seen in your homes. You have a room heater, right? The coil inside glows bright red hot, but the wire connecting it to the plug point stays completely cool. Ever wondered why? The same current is flowing through both. By the end of this session, you'll know the exact physics behind this. Here is our plan for today. We'll start with this simple question. Understand what's happening inside a wire, get to the main formula, and then clear up some common mistakes. We'll go step by step, making sure everything is crystal clear. Okay, so let's focus on our main puzzle first, the heater. This one single question is going to set the stage for everything that follows. It's the key that unlocks the whole concept. Now, to solve this mystery, we have to shrink ourselves down, way down, and go inside the copper wire. We need to see what the electrons are actually doing in there. Let's see how this builds our understanding. So what do we imagine? We think electrons just flow in a nice, neat, straight line, right? Like cars on an empty highway. But that's not what happens at all. The reality is, it's a total mess in there. It's more like a game of pinball. An electron starts moving, but bam, it collides with an atom of the wire. Then it changes direction, and bam, it hits another one. These atoms, they're fixed in their positions in what we call a crystal lattice. So we call them lattice ions. The poor electron just zigzags through, constantly bumping into them. This brings us to a super important term for your exams, Bacho. It's called relaxation time, and we use the Greek letter tau for it. It sounds complicated, but it's a very simple idea. It's just the average time an electron gets to, relax or take a break between two hits, between two collisions. It's the tiny gap of time it gets before it hits the next pinball bumper. Okay, so now we have this mental picture, this pinball game happening inside the wire. So let's learn the secret code, the formula that physicists use to describe this entire game mathematically. Right, so this difficulty that the electrons face, this opposition because of all the collisions, this constant bumping around, it has a proper physical name. We call it resistivity. The symbol for it is the Greek letter rho. It's simple. The more collisions, the more the opposition, and so the higher the resistivity. So, what things affect this resistivity? Well, think about our pinball game. First, the mass of the electron, m. If the pinball is heavier, it's harder to get it moving, right? So higher mass means higher resistivity. Second, n, which is the number of free electrons per unit volume. If you have more pinballs, more electrons available to carry the current, it's easier. So higher n means lower resistivity. And finally, our new friend relaxation time tau. If the electron gets a longer break between collisions, it can speed up more. So longer relaxation time means lower resistivity.
And here it is, the master formula that ties everything together. Resistivity rho is equal to m upon N squared tau. Bacho, please note this down, it's very important. This formula is the reason we know why copper is a great conductor and why something like nichrome is great for making heater coils. It's all hidden inside these atomic properties.
Okay, so we have the formula. Now let's use it to explain something we see all the time. What happens when a wire gets hot? Let's see why temperature is the real boss here. Just follow the chain of events. It's very logical. 1. You increase the temperature. What happens? 2. The lattice ions get more energy and they start vibrating more and more violently. Imagine the pinball bumpers are now shaking like crazy. 3. If the bumpers are shaking, it's much more likely an electron will hit them, so the collisions become more frequent. 4. If collisions are more frequent, what happens to the break time between them? It becomes shorter, so relaxation time, tau, decreases. And 5. Look at our formula. If tau is in the denominator and it decreases, what happens to the whole value of rho? It increases. See? It all connects perfectly. And this isn't some tiny effect, For a normal copper wire, if you just heat it from room temperature, about 20 degrees Celsius, to the temperature of boiling water, 100 degrees Celsius, its resistance increases by a solid 32%. That's a really significant change. Okay, now for a very important section. Please listen carefully. Let's talk about two common mistakes, what I call the silent killers, because they quietly take away your marks in the exam. First mistake. So many students write this. Higher temperature makes electrons move slower. This is completely wrong, and your examiner will cut marks for sure. The fact is, the electron's random jiggling speed actually increases with temperature. The real problem is that the collisions become so frequent that the electron's net forward movement, its average drift, is reduced. Think of a busy road. The cars might be fast, but if there's a huge traffic jam, the overall flow of traffic is very, very slow. The problem is the jam, not the car's engine. And here's the second silent killer. Students think that because resistivity is a property of a material, it must be a fixed constant, like, say, the charge on an electron. No, that is not true. Resistivity is a property, yes, but it's a property that can change, and it changes a lot with temperature. So it is not a universal constant. The resistivity of copper is different at different temperatures. Please remember this.
All right, let's quickly summarize everything we have learned and see how this topic connects to the bigger picture of electricity.
So, here are the 4 most important points to take away. 1. Resistivity is because of collisions. It's not some magical friction. 2. The master formula, rho equals m upon n e squared tau, explains everything. 3. For metals, temperature up means resistivity up. And 4, and this is a big one, this entire idea of collisions is the microscopic reason why Ohm's law actually works.
And so, finally, we can solve our starting mystery. The heater coil and the cord both have the same current, I. But the coil is made of a special material called nichrome, which has a very high resistivity. The cord is made of copper, which has a very low resistivity. And you know the formula for heat is I squared times R. Since the resistance R of the coil is huge, it produces a huge amount of heat and glows red hot. The copper cord has a tiny resistance, so it produces very little heat and stays cool. It's all about the material's inner pinball game.
And I'll leave you with one final question to think about. If all this resistance is because of collisions, what would happen if we could create a material with 0 collisions? Imagine the pinball bumpers just stopped shaking entirely. What would happen to the resistance? Well, that very question leads us to the amazing world of superconductors, which we'll study about later. I hope this was all clear. All the best.